Hello students! We've done a lot of things with linear transformation so far, but one thing we haven't talked about yet is inverses. So it's time for us to talk about them. So let us begin. So how are we going to define the inverse of a linear transformation? Well, we'd like to define it in a similar way that to what we did for groups and fields and things like that, which is we have something that takes us back to the identity. So what is our identity here? Well, you might remember that for any vector space, we have an identity defined by that, right? We showed that this is a linear transformation. It's easy to show. You can show it again. But this map, and it doesn't matter what my vector space is, this map always is a linear transformation, and this is how we define our identity. Sometimes there'll be two different vector spaces, and if you want to talk about the identity in a certain one, like let's say I had a v and a w, I could always do an I subscript v or something like that. And we might actually want to do that here to make sure we know what we're talking about. So what is an identity? It's something that brings, and what is an inverse? It's something that brings us back to the identity, right? Just like with a group or with a field. So what are we going to do here? Well, we'll say the inverse of a linear transformation T from V to W is a map. By the way, I'm not claiming the inverse exists because there might not be an inverse, but I'll just say the inverse would be a map S from W to V. And I should say linear. Linear, it also has to be a linear transformation from W to V. By the way, linear map, linear transformation, same thing. So that T of S equals I and S of T equals I. Okay, so let's think about what this means right off the bat. Okay, so over here, this is composition, right? So this would mean I start off with something in W, because we start on the right here. I go to V, S maps W to V, and then I go into T, maps from V back to W, and I get back to what I had to begin with, which is in V or W. Take a moment to think about it. You can pause if you like. It's in W. I started in W, I went to V, I went back to W. So this would have to be the identity on W. And here, well, if I'm doing T first, V goes to W, back to V, this would have to be the identity on V. So that's what this means. You could condense it into one line if you're willing to abuse notation, but you have to accept that your I would mean different things, right? We didn't have that problem with groups. We were all in one single set. We don't have that problem with fields, but here we can be a little bit careful. Okay, so what can we say about inverses? And the first thing is we're not going to claim they always exist, but if the inverse of T exists, then it is unique. Now, whenever you're trying to show uniqueness, there's a couple ways we could do it. We could assume that there's some transformation T that has two different inverses, and then we could show they're the same, coming to a contradiction. Or we could just say, hey, suppose T has two inverses, S1 and S2. They must be the same. And this means for any two inverses, they must be the same. And that also shows that all inverses are the same without having to go through the extra contradiction step at the end. So let's suppose S1 and S2 are both inverses of T, which I could say goes from V to W. I could also write T is in the LVW notation, right? T is in the collection of linear maps from V to W. I could do that as well. but I kind of like to draw the arrow. I like the action of the arrow there. So suppose S1 and S2 are both inverses of t. Okay, I want to show that they're the same. So how could I show that they're the same? Well, let's start with 1. And let's try to think. I have no indication as to where I should go, but I do know a few tricks, and one of the tricks is you can always multiply by 1 or add 0, which really means the trick is you could always multiply by the identity or apply the identity. So let's apply the identity. And what do I know? Well, I have S1 is equal to S1I. Now, even in Scratch work, right, what we could say is we could say, okay, well, what do we know about S1 and S2? I know that T S1 is I, S1 of T is I, T of S2 is I, and S2 of T is I. So I have 4 different things that I could plug in here, right? This is what we know. This is what we know, because this is the definition of saying S1 and S2 are inverses of T. So which one of these things should I plug? And I'm just saying, hey, I don't know what I'm doing. Maybe I'll plug something. Well, let's think about it. I would like to get an S2 somehow, right? Because I want to get S1 equals S2, so that rules those out. So I could either turn this I into an S2T or a TS2. And I think I like that one better. S1, T, S2. And the reason I like this one is this one's going to allow me to use associativity. S1 and T cancel each other out. Give me I, S2, which is equal to S2. I showed that S1 and S2 were the same, so I'm done. We assume that they were both inverses. They must be the same. For any 2 things that are inverses, they must be the same. Therefore, there can only be 1. That is my proof. Okay, and of course, since we now know that there is only 1, when there is 1, we'll give it a name. If the inverse of T exists, well, we already call it the inverse, but we can write that symbol. So we're going to write T inverse for our S. So instead of just saying, hey, the inverse of T is S, we can use this symbol, T inverse. Okay, so that's the basics. That's the definition of an inverse and a proof that inverses are unique. And we have our new notation. And there's plenty more that we can do with inverses coming up.